In this video, I'm going to introduce you to Euler's formula. This is one of the most famous formulas in all of mathematics. It's related to complex numbers, and for the Fourier transform, it will provide a compact notation for representing detailed information about the signal. It also directly leads to what many people consider to be the most beautiful equation in all of mathematics. Simply put, Euler's formula states that e to the ik equals cosine k plus I sine k for any real number k. The e here is the natural exponential, which is the number 2.718 and so on. It goes on and on forever. It's an irrational number, so it has no pattern with it. This is a famous constant in mathematics, and it pops up all over the place. In trigonometry, complex analysis, differential equations, simulations, biology, even in finance, you'll find this constant e. If you make a plot of e to the x, you can see that for negative numbers, it gets very small but stays positive, and for large positive numbers, it quickly blows up to infinity. In fact, the derivative of e to the x is e to the x. In other words, the derivative of the function is the function itself. That's quite a special property, although that's actually not what we care about here. What we care about here is what happens when you put an imaginary number inside the exponential instead of x. This gives us e to the ik, where I is the imaginary operator that I discussed in the previous video, and k is some number. It's sometimes given as phi or theta, but here I'll just use k. So Euler's formula says that this expression is equal to cosine k plus I sine k. That's a neat formula for a number of reasons, one of which is that it provides a direct link between complex numbers and trigonometry. In particular, if you think about an axis with cosine and sine defining the two axes, then all values of k are somewhere on this unit circle. That might sound familiar from the identity that cosine squared plus sine squared is always equal to 1 for any value inside the cosine and sine function. So all values of k are on this unit circle, and e to the ik describes a unit vector that goes from the origin to that point on the circle with angle equal to k. Therefore, Euler's formula describes a vector in the complex plane, and the k in the exponent gives the angle relative to the positive real axis. Let's have a look in MATLAB before moving on. So here you see a plot of e to the k. In MATLAB, the natural exponential is given by the function exp. So this reproduces the figure that I had in the slides. This code here illustrates that for any value k, the plot of cosine k by sine k is a number on the unit circle. You can try this yourself. I encourage you to pause the video and change these values of k, and you'll see that no matter what k is, even if it's an extremely large number, it will still be somewhere on this unit circle, including negative numbers. Let's change this back to, for example, pi over 3. And now in this code here, what I'm going to do is have that same value k go into Euler's formula. So this is e to the ik. And now I'm going to plot that line using the angle defined by this complex number. And you can see that the line goes straight to that point, which here we defined using the cosine and sine of that point. The exponent k indicates angle in radians. So that means that this angle here is e to the I0. This point here is e to the I pi over 2. And this one here is e to the I pi. And if you think of Euler's formula as a function of x, then this vector here tells us that when the angle is pi, the x-coordinate is -1. Or we could rewrite this as e to the I pi plus 1 equals 0. This is a pretty remarkable formula because it contains 4 of the most important numbers in mathematics: the rational numbers 0 and 1, and the irrational numbers e and pi. It also contains 3 fundamental arithmetic operations: addition, multiplication, and exponentiation. And that's why many people believe that this is the single most beautiful and elegant mathematical equation ever discovered in human civilization. That's not really so important for learning the Fourier transform, but it is pretty interesting, so I thought it would be worth the little tangent to introduce this. So far, I've only been discussing unit length vectors. In other words, vectors are points that lie on this unit circle. If you want to use Euler's formula to describe a vector that's longer or shorter, in other words, that extends beyond or is shorter than the unit circle, you have to multiply the vector by some scalar. Let's call that scalar m for magnitude. This scalar m is a single number. It doesn't change the direction of the vector, it only changes its distance from the origin. And that gives me to the ik, where m is the distance to the origin. You can see that in all the previous examples, m was implicitly set to 1. Writing this out in Euler's notation gives us m times cosine k plus I sine k, or me to the ik equals m cosine k plus m I sine k. In a previous video, I told you that a complex number has two key pieces of information that we need for Fourier analysis. The magnitude of the complex number, which is the distance away from the origin, and the angle with respect to the positive real axis. And those two crucial pieces of information are listed here in Euler's notation really clearly and really simply. M is the magnitude and K is the angle. This is why Euler's formula is so practical for Fourier analysis. You just read the critical information right off the number. And a little bit later in this course, I'm going to start calling numbers of this form a Fourier coefficient, which is the key result of the Fourier transform. Now, to make this a little bit more concrete, I'm going to use Euler's formula to plot some vectors in the complex plane in MATLAB. So here you see in this code, I'm defining m and k, and then I create this complex number using Euler's notation m e to the I k. And then I extract the magnitude of the number, or the distance away from the origin, as the magnitude of the complex number. And remember from earlier that this is equivalent to saying the square root of the real part squared plus the imaginary part squared. And here I extract the angle relative to the positive real axis using the MATLAB function angle, which is equivalent to computing the arctangent or the inverse tangent of the ratio of the imaginary component versus the real component. I encourage you to pause the video and change these values a bit to see how the plot changes as you change these different values of m and k. So in this video, I introduced you to Euler's formula. The key idea is that we will use Euler's formula to encode two critical pieces of information about complex numbers that we need in the Fourier transform, the magnitude and the angle with respect to the positive real axis. I haven't yet told you about how to obtain these complex numbers and how to interpret them. First, you need to know a few more foundational topics like sine waves and the dot product, and these are the topics of the next videos.